I should also thank all the members of Mila and IBM Machine Translation team. So I usually get a question. So this is going to be my overview. I will first talk briefly about neural machine translation. I'll give an introduction, very brief introduction about sequence-to-sequence learning, and then sequence-to-sequence learning with attention. And then I will delve deep into multilingual neural machine translation. I will explain our model, and then I will show you some experimental results on large-scale, low-resource, multilingual neural machine translation. And then I will talk about multi-source decoding and training strategies for multilingual models. And then at last, I will talk about zero-resource neural machine translation. And then I will conclude my talk with some future directions, like how we can use these models to do system combination, or can we extend it to do larger context neural machine translation, or even zero-shot neural machine translation. I usually got questions how I ended up doing neural machine translation. So I thought maybe I should put the slide. This is the whole. This bar is my PhD timeline, and from my perspective, I've been trying to model spatiotemporal data all the way beginning from my PhD. And I was back in 2011. We were doing representation learning. Back in the days, it was called unsupervised pre-training, and then you have a pre-trained model. You just initialize your model with this pre-trained model, and then you fine-tune according to your tasks. I started working on sparse coding, autoencoders, and then with AlexNet, we started working on convolutional models. And I was applying these techniques to sequential spatiotemporal data, such as fMRI data, which is you're given sequences of volumes, and you've been asked to predict the output, either stimuli or another task. And then in 2014, I went to Yoshua's lab as a visiting PhD student, and at that time, NeuralMT was in its crawling step. It was taking its crawling steps. And Yoshua asked me, what do you want to work on? I told him that this is the topics that I've been working on. And I should tell, fMRI is a really, really low resource problem. You only have tens or hundreds of data. So Yoshua suggested me maybe you should work on low resource neural machine translation, which is an unsolved problem. And then I started working on low resource neural machine translation. This corresponds to this red bar, the intersection of blue and red bars. And then we had a meeting right before 2014 NIPS. It was about multilingual neural machine translation. And one of the moments of the talk was, okay, this seems like a really low-hanging fruit. Maybe we should first prove that NeuralMT works, and then we can focus on the multilingual neural machine translation. And then we participated in a lot of challenges just to prove neural machine translation actually works. We started working on IWSLT for Turkish and Chinese. We ended up not submitting. But we ended up having pretty good models for Turkish. And the way we tackled with these two low resource languages, by the way, this is the low resource by the domain of IWSLT. It's not low resource in general, but the domain of IWSLT. We ended up this idea about diffusion. You pre-train a language model, continuous-based language model, and then you plug that language model into the decoder of your sequence-to-sequence model. It derives the translation as you generate. And this diffusion idea came right after the IWSLT submission, and then we used this idea in OpenMT challenge for Chinese English, and we were doing fairly okay, but we couldn't actually put the nail on the coffin that NeuralMT actually no one was convinced. So we decided maybe we should participate WMT15 challenge on 5 different pairs. Czech English, German English, and the other ways, and Finnish English. Luckily, we managed to get good results. And right after WMT15 submission, I had 5 or 6 months left at Montreal, and we decided, okay, the multilingual neural machine translation is a short, low-hanging fruit, and you can solve this problem in 5 months. It didn't end up that way. It took me almost a year to actually make this model working. And at this point, I started working on multilingual neural machine translation. Right at the end of 2015, we ended up having a working model. And I started my internship at IBM. I worked on multi-source and zero-resource translation. And at that point, we came up with zero-resource translation. And I'm here right now. OK. Now I'm getting into neural machine translation. So I think we all know about the Warren Weaver's memorandum on translation. He was making this analogy about if you want to communicate between two towers, you shouldn't be shouting to each other because you cannot reach out. So what you should be doing is going down to a common basement and then exchanging the information in that common basement, common space. And this common space is this whole road, let's say the highway or something. And he was calling this common space interlingua. All the stuff that I will be talking about in multilingual neural machine translation is how are we going to model this interlingua, this highway. We already know how to going down from the top of this building all the way to the interlingua by using an encoder, and we also know how to go up from the interlingua to the top of the building by a decoder. And I will talk about how are we going to model this interlingua, this common space. Let me talk about the basic encoder-decoder model without any attention. We are given a source sequence. We are using a language model, which is basically a recurrent neural network in this case. We are summarizing this input sequence into a fixed length hidden representation. And then from this hidden representation, we are using another language model, but this one is a conditional language model, which conditions also on the summarized representation of the source sequence and generates one token at a time. This is the basic encoder-decoder architecture in a nutshell. There's a basic problem here. If you use a fixed length vector to represent the meaning of a whole sentence, you will end up with a huge bottleneck, with a terrible bottleneck. So the remedy came from the idea of using an attention. This is the sketch of a neural encoder-decoder architecture with attention. Here again, we summarize the source sequence, but in two directions, from left to right and right to left, by using a bidirectional recurrent neural network. And then at each time step, the decoder is again a conditional language model. At each time step of the decoder, when we generate a token, we look at the weighted average. We look at the whole set of vectors of the encoder. This is called the annotation. We can call the whole vector set here the annotation set. And then we have an attention module here, which gets the query from the decoder by looking at the decoder's hidden state, and gets and looks at the annotations of the encoder, all these hidden vectors, and then generates a distribution, alpha distribution here, and then takes the weighted average of all these context vectors and passes that information into the decoder. And this is the encoder-decoder architecture with attention. It iterates on two steps. First, it computes a relevance score for each annotation, and then uses the weighted sum of the annotations as the context. It basically consists of three modules: one encoder, the red box here; one decoder, the green box here; and the attention module here, the green box. So the blue box and the green box. And how it aligns with the Warren Weaver's analogy, we can think this building as the encoder, this building as the decoder, and this common space is represented by the alignment function. And we can also make another analogy. Maybe this alignment function is how a car behaves between how the car goes from this point to this point in that interlingua. So the question is, how are we going to model this green area when we have multiple encoders and multiple decoders? Are we going to use a separate attention function across all these source and target pairs, or how are we going to deal with that problem? And here we represent this green highway by using this cloud, and our aim to translate from any of those languages to any of those target languages. There were some attempts to do this. Chronologically, it all started with the with work which was published in ACL 2015. And in this model, they had only one encoder and multiple decoders, but they had a separate attention module for each one of those decoders. So for this decoder, when it wants to, it needs an alignment distribution. It was asking this attention module to give the right alignment distribution and the context vector. And the same thing happens with decoder 2, but it was using a separate attention function. In this setting, the problem is when you want to introduce another decoder, you also need to have you also need to introduce the attention module as well. And the experiments were a bit small scale. They were only using Europarl. So we were not actually convinced about, okay, this multilingual neural MT works. And then a paper from Google and Stanford came from Long et al. It's published on iClear 2015. They did not only focus on multilinguality, but also they trained the model in a multitask fashion. They were not only translating from German to English, but they were also doing some constituency parsing and so on. But they dodged the bullet by not using any attention module. So they were using the basic encoder-decoder architecture. And if you're not using any attention module, so you're basically removing this highway, and you can think of it like you stitch your buildings together, and the common space is just a point. The common area, the interlingua, is just a point that you summarize all the information from one encoder to be decoded from the other building. And the multilinguality was, again, not considered in depth. They were only considering English to German and the other way. And lately, there was another paper presented this year, Knuckle, from Kevin Knight's group. They were focusing on multi-source translation. All these previous work, they were using by text. They were using as their training data source language and its corresponding target language. But in the many-to-one setting introduced by Zhou et al., they were using multi-text. For example, they were using French and German at the same time to translate into English. This necessitates multi-text, obviously. And they showed the experiments on some small-scale subset of WMT15 corpus. And, but they showed some impressive improvements in terms of BLEU. These are the chronologically review of the recent work. So the question is, how are we going to increase the number of encoders in this case? How are we going to reduce the number of green boxes in this case? How are we going to introduce a green box here? And how are we going to reduce the green box here in this case? So we want to have a model that is able to do all these stuff, but also we want our model to be scalable. So we thought that maybe we should model the cloud, this green box or the interlingua, by using a single parametric function that is shared across all these source and target pairs. And this was the basic idea. What we can do if we share this attention function across all the source and target pairs, it's going to be a small step to finding an interlingua. If we can model this interlingua by using a single function, then it will tell us something about the practical modeling of this interlingua. And it will be a step towards the universal attention mechanism, We will focus on text-to-text translation, but if we can prove that the universal attention mechanism actually works, maybe we can extend it to other modalities as well. So this is just a proof of concept by using text-to-text translation. And if we share only one attention model across all these pairs, if we succeed on modeling this interlingua, then we can actually generalize to the unseen parts of this highway, right? The cloud. We can maybe generalize the unseen part of the cloud, and that will bring us the positive language transfer. And it will potentially trigger further research as we will explore different decoding strategies, different ways of using this multilingual model by using a single attention module. So this is the conclusion slide, actually. The first question was, can we actually share a single attention mechanism across all these pairs? The answer is yes, we can do that. And in which cases will that be useful? It will be useful when we want to transfer into resource-poor languages. We will always see improved performance when we are doing low-resource translation. And when the target is English, we will also see improved quality. And I will get into the details of why we see this improved quality when we translate into English. And how are we going to train such big model? It's going to be a pain, but we're just going to use SGD. We're going to maximize the joint loc likelihood, and we're going to wait 3 weeks for one model or a month. And it's going to be a prerequisite step to do out-of-the-box multi-source translation, either multi-source training or multi-source decoding. It will be, again, a prerequisite step towards zero-resource translation. And you can also use this model to do some multimodal sequence-to-sequence modeling. So let me remind you the architecture again. Here we have the red box as the encoder, the blue box as the decoder, and the green box as the attention module. And we're going to increase the number of red boxes and blue boxes, but we're going to keep only one green box all the way. And this is the overview of the model. It looks a little bit complicated, but it also consists of 3 modules. This is the encoder. We only have one additional operation here on top of the bidirectional recurrent net. And the decoder is exactly the same that we were using in the regular encoder-decoder architecture, but we have a slightly more complicated attention module, which I will get into the details shortly. Here in this model, the basic idea is do not let any information passing through encoder to the decoder without going through the cloud. So the cloud here is represented by these green boxes. They are all parametric functions and implemented as feed-forward neural networks. I will get into the details of the attention module shortly. Okay, what we end up is increasing number of decoders and encoders, and it looks something like this. We will have multiple encoders, multiple decoders, but only one attention module. The attention module will learn to stitch any encoders with any decoders. What we can build with this model, we can either build a multi-encoder. We will have multiple encoders, one attention module, one decoder. This is usually the case when we translate from all the languages into English. Or we can build the multi-decoder model. We have one English encoder usually and the target languages. Or we can build a multi-way model when we have multiple encoders and multiple decoders. I'm giving this slide just to give you the terminology that I will be using. So what we end up is a crucial idea. It's a very important point. That is the idea behind all this multilingual work. We're not trying to model the behavior of individual cars. We're trying to model how the highway works. So we're not going to focus on learning a shared semantic space that all these languages are represented. But we're more interested in learning a function that traverses an intrinsic space and stitches these encoders with the decoders. And it will not have a fixed semantic space, but it will be a mechanism, and we will use this mechanism as an API throughout the multilingual modeling. As I just told, we train a function that learns how to glue any encoder with any decoder. So hypothetically, it learns to traverse an intrinsic space. That's why we don't have any explicit regularizer that contracts 2 points if they're semantically similar together. It is computationally beneficial. This is arguable, but it's computationally beneficial when you consider, think about you added another language pair into the whole mix of encoder and decoder into this multilingual model. You need to also introduce all the alignment functions between the decoder and all these encoders. But if you share this attention function, then you don't need all those attention functions. If you do so, you will end up with a quadratic growth on the attention parameters. But if you don't, if you share, the parameters only grow linearly. But I should also tell that the number of parameters in the attention module in this implementation is quite small, but that's a matter of that's a fact that the type of encoders and decoders that we're using. Think about you're using a character-based encoder and you're using a convolutional encoder. Then the number of parameters in the encoder will be quite small, and when you want to use a highly sophisticated attention module, you need to increase the capacity, and then this growth will be very significant. And what's in it for us? We will get the language transfer if we share this attention module, because maybe seeing all these examples, this module, this mechanism can generalize hopefully to the unseen parts of this highway. These are the premises. So let's look at the details of the shared attention module. In the regular encoder-decoder case, we were looking at a fixed dimensional hidden vector. But in the NMT model with attention, we have a context set. Here, I called it encoder annotation set, CN here, for the encoder N. So we have a set of annotations, H1 all the way up to the sequence length of the encoder. And the attention module is going to be used as an API. It will get the query from the decoder by using by this small neural network. It will get the query, and after getting this query, it will generate the alignment distribution over all these elements in the annotation set, and it will get the weighted average of all these annotation vectors. And then it will apply another transformation. This is a shared transformation again. And then we will end up with the context vector here to be used by the decoder to generate the next token. This is how the attention module works. All these small boxes are parametric functions, and they're implemented as feed-forward neural networks.
So FADP is the thing that's not in the normal one, in the baseline?
Yes. Okay. Yes. Yeah, this is an additional computation that we introduced here.
But is it directly related to the idea of shared attention, or is it?
Yes,
is it so that you can get into the same semantic space?
Exactly. Yeah. So if we don't use this, then the representation, the weighted average here, will be unknown for a decoder that has never seen that encoder before, right? Yeah. So we have to actually use another transformation here, either linear or nonlinear, to map it into a common representation or something.
I mean, have you tried, like, you can do it before just easily, right? Do you know, have you tried that, like doing it before the summation on each? I guess it's just more expensive
to do
on each.
These
I'm saying do it on each H before and then sum up after, like fitting it through another.
I haven't tried that. Any other questions about?
So that means you are actually modeling a shared semantic space.
But this is done at each time step.
I see.
So it's going to be a function, not a fixed dimensional space. This is going to be a time-dependent context vector.
But conceptually, like it's the features, represent the same thing.
Yes, that's why we call this the intrinsic space, that it learns to traverse this intrinsic space. Yeah. So formally, we have n encoders, n source languages, m target languages, And we are going to use only bilingual corpora to train this giant model. So we don't necessitate any multi-text. We are only going to use bilingual corpora to train this model. And we're just going to maximize the joint log likelihood by using this cost function. So we end up with a model that has n encoders, m decoders, and a shared attention mechanism, which consists of two functions, f-score and f-adapt.
Does it require n-way bilingual corpora, or can you be missing some?
You can be missing.
Okay.
Yeah, you can be missing. Most of the time, we miss that. You know.
Yeah.
Yeah. What we usually have is all the languages to English and the other way. We never have a bilingual corpora between Finnish and German, if you're not going through pivots. But I will talk about that later in my talk. Okay, how are we going to train this model? By using only bilingual, by using only bytext. As I told you, we are using only SGD, but preferably with some smarter step rules like ADAM or ADA delta. And we're going to update one pair at a time. After updating that pair, we're going to switch to the next pair, and then we will do this in a round-robin fashion, one update at a time. So how does that work? For example, we are using the bytext between encoder 1 and decoder 1. We are going to do the forward pass. We're going to update the parameters here, and we're going to skip to the next language pair, which uses the bytext between encoder 2 and decoder 1. And then after doing the update, we're going to skip to the next one. And if we have multiple decoders, then we will we will skip to the next decoder, and then we will do the updates in a round-robin fashion again. We tried a lot of scheduling techniques here, but it turned out a round-robin fashion with an update scheduling of one works the best across all these random scheduling or some other heuristic schedules.
Do you have like roughly the same amount of data in each language?
No, and that will cause a lot of problems.
Sorry.
Yeah.
I can talk about that. Like.
Yeah, I will talk about how to tackle those problems as well. So we started with this controlled experiment. We started with this small model, having 3 encoders, English, German, and Finnish, into German and English. Can you guys guess why we chose these languages? Yeah, WMT15. We participated WMT15 by using these languages, and we already had pretty good encoders and decoders, pretty good baselines to compare with. And we realized after some initial experiments, it was actually helping on low resource languages in particular. So we thought that, okay, maybe we should focus on low resource languages and do some simulated experiments. And that's why we reduced the amount of data that we're using in the bytext to 5, 10, 20, and 40%. And for example, we reduced the amount of data in the English to German pair to 5%, and use all the available data in the other pairs. And then we train this model jointly all together by sharing the attention module and see the effect on low resource translation. And this is the results for the low resource translation. Let me describe the table first. So the first rows corresponds to Finnish to English translation. And the first column is the amount of data that we're using. 5% of the data corresponds to 100K parallel sentences. And the single column corresponds to the experiments when we train only a single pair neural machine translation system. It's the vanilla neural MT system. What happens when we use this amount of data and train a single pair neural machine translation model? And single plus DF. DF stands for diffusion. As I talked in the beginning of my talk, so diffusion is a basic idea. It actually learns to nonlinearly interpolate and gate by using a language model, decoder-side language model, and the hidden state of the decoder. So this is the hidden states of the decoder. This is the hidden states of the language model. This is a recurrent language model, and we have an additional neural network that learns to interpolate between these two hidden representations, and then it generates the output distribution at each time step. This is the idea of diffusion. This column stands for diffusion, just to see if the improvement is coming from using additional monolingual data or not. And the last column stands for the last column is for the multilingual model. And in each cases, we see an improved performance in terms of blue when we use multilingual model. And it can be up to 3 points, for example, when we translate from German to English. But the improvement will be a little bit smaller when we translate into English to German. As I told at the beginning, we will always see improved performance on low resource languages, and we will also see improved performance when we translate into English. But it's not true on the other direction. For example, for English to German, this is low resource. This is still low resource. That's why we are seeing some improvements. But we're not going to see that improvement when we translate from English to other languages. And I will describe why we are seeing this trend and how are we going to tackle with that. Yes.
Did you also evaluate on English to English and German to German?
Yeah, but autoencoder criterion in the encoder-decoder architecture with attention, it's not easy to handle because it learns to copy rapidly, and you will lose a lot of capacity just learning how to copy.
So did you skip those when in training?
I did some scheduling on the autoencoder paths. For example, after 1 million updates, start training English to English path, or add some noise in the inputs, embeddings, or even the alignments of this English to English path. But I couldn't manage to make it work for the models with attention. There are some work that they managed to make it work without attention, but with attention, you're increasing the bandwidth, and it's going to be very easy to learn how to copy.
For each multilingual model, you use the same percentage of available data for each language pair, right?
Yes.
So if it's 5%, you're using 5% of Finnish English, German English.
No.
German,
If it's 5%, it's only limited for the Finnish English.
But you're using all the available data for
the other pairs.
Got it.
Yeah. And we trained the language model here in the diffusion case by using all the available English target site data on the other pairs. Okay, so, and then Cho convinced me to do the experiments on all the pairs of WMT15. So in WMT15, we had 6 languages, English, Czech, German, Finnish, French, and Russian. This is in no particular order, by the way. But we end up with having 2 giant models, one multi-decoder model here on the left, and one multi-encoder model here you see on the right. We're going to train a model which has 10 pairs, and we're going to share a single attention module between all those source and target pairs. And it doesn't scale well, so we couldn't fit it on a single GPU when we first started. Nowadays, with some tricks, you can actually put it on a single GPU. But we distribute it on 2 GPUs. And we trained all these 6 language pairs, all these 10 language pairs. And as I just told, it essentially consists of one multi-encoder, one multi-decoder jointly trained with the shared components. Essentially, it halves the number of parameters in the whole set of single pair models. And we haven't increased the capacity of the attention module, although we share it across all the 10 pairs. It was a beautiful coincidence. I was training these models on NYU machines, and those machines were named Weaver machines after Warren Weaver. So how we train this model, we put the multi-encoder in one GPU, multi-decoder in the other GPU. And we replicate the attention parameters in both GPUs. We do the forward pass. We compute the gradients, we exchange the attention, we exchange the gradients of the shared components, we do the update locally, and then we do the next update. This is how we train the model on 2 GPUs. So one crucial point is you should be sharing, so here we exchange the gradients, right? The gradients that you exchange should be compatible. For example, you shouldn't be exchanging gradients between English to Czech, and German to English. You should be exchanging the gradients between English to Czech and Czech to English. That will also help you to get the reverse direction, the reverse information about the alignment, right? And this, yeah.
I don't understand what you mean by that. Like, you have to exchange the gradients that are needed by the other model, and like, are you just saying as an implementation trick you don't have to, or?
If you don't do this, it behaves.
I mean, yeah. If you don't exchange, yeah, I mean, it'll become divergent if you don't exchange all the gradients that need to be.
Yeah,
but
the training oscillates like crazy.
But I mean, are you doing anything right in this that's an approximation, or is it exactly equivalent to training it on one GPU? It's just an implementation trick that you're doing.
This is an implementation trick on 2 GPUs. But this is a free lunch that you get alignment biases, like structural alignment biases. You also get the reverse information, the reverse error signal of the alignment. For example, when you translate from Czech to English, you will also get the information from English to Czech. So, and then you will do the update by considering those two at the same time.
Oh, you're saying you sum for many batches actually in both directions, and then.
Sorry?
You're saying that you sum the gradients in.
Yes.
Oh,
yes.
okay.
Yes. Yeah.
So you do English Czech on one CPU, and you do Czech English for the same data?
No, not for the same
Just,
data.
but the same language
they're-
by different many batches?
Yeah. They shuffle differently, but the size of the sequence lengths were approximately the same. Otherwise, the one waits for the other to complete. Yeah.
And then you exchange and you average the gradients.
We sum the gradients and then do the update. How we train it, we pass through the, we were looped through all these languages on 2 GPUs. For example, on one GPU, we're going to do the forward pass on English to Czech and Czech to English. We do the update and skip to the next one, English, German, German, English, and English, Finnish to English. And all the way to the end, when we finish all these language pairs, and we will wrap back to the Czech to English pair. How does this model behave? Without any tricks, without doing any balancing between the data sets or doing any additional stuff, this is the initial results that we get. So let me explain the table here again. The first rows corresponds when we translate from French to English and English to French. This is the amount of data that we are using, and it's in decreasing order. And this second column stands for the blue scores, and the first column of the blue column, the single column of the blue column, stands for when we train a single pair model by using this amount of data in this pair. For example, this uses 39 million bytex to train a French to English model. This is a vanilla sequence to sequence model with attention. So we have 10 models here, 10 separately trained models, but in the multi-column, all the numbers are coming from a single multilingual model. We train one model, and these are the scores of that model on all these source and target pairs. We also provide the negative log likelihood, because we can see something interesting when we look at the log likelihoods as well. What we see in this table is, when we translate into English, we always see improved performance compared to the single pair models. For example, in all the cases, multilingual model performs better when we translate into English. But it's not the same when we translate from English to all the other languages. In terms of log likelihood, they're quite close. Even if it's not better, they're quite close in terms of negative log likelihood. But in terms of these are all test set log likelihoods, yes. The blue scores and log likelihoods are all on test set. Although the log likelihoods are quite close, we don't see the same effect on the blue scores. And why are we seeing this trend? When we translate into English, we're seeing improved performance, but not the other way. I will describe it shortly. And then we saw that, okay, this model is working fairly good in low resource languages. Maybe we should analyze on the real low resource language pairs. That's when I started doing my internship at IBM Watson. So we experimented on 2 language pairs. First one is Uzbek English. this is a really low resource language pair because we only have 75k parallel sentences. We use byte-pair encoding and with a vocabulary size of 40k. And for Turkish, we compiled our own data set using all the available byte text on the web. And we ended up with a data set of size 0.8 million. Sorry, 0.8 million. It's 800,000 parallel sentences. We use the same amount of, we use the same vocabulary size, and we use byte-pair encoding in to learn the vocabulary. We evaluated on BLUE, TR, but we early stop on TB score. TB score is just the average, it's just TR minus BLUE divided by 2. We will early stop on the TB. Previous experiments, we always early stopped on BLUE, but on these experiments, we will early stop based on TB score. Stands for T minus BLUE. We also introduced some additional information to the decoder. For example, we also gave the information about which encoder that you're translating right now with a one-hot encoding of S, like here, as it's a one-hot encoder of the source encoder. And we also provided it here to the initializer network. This is just a small detail. So in this table, first let's look at the Uzbek English translation. It's the first row. And we can focus on the test column and the single pair results. The one in the parentheses stand for BLUE, and the other one is TB score. For TB, lower is better. For BLUE, higher is better. And when we train an Uzbek English model without multilingual, without any other pairs, this is our baseline. It's a really low baseline. We are getting 6.45 BLUE scores. When we introduce Turkish to English into the mix as an encoder, we are getting a huge jump, almost like 3 points. These are, again, by the way, in the test set, we're getting 3 BLUE points improvements when we introduce a Turkish English as the additional language pair. By the way, Turkish English is also a very low resource language. We were using only 0.8 million byte text, but we see a huge improvement here. And when we add Spanish English, which is using almost 30 million byte text, this is a really high resource language pair, Spanish to English. It improves a little bit further, but not super good improvement. But this is the best score that we get by using the single pair models. And we hit the 10.39 BLUE scores. And after we thought that, okay, what will happen if we remove this high resource pair and then just use the reverse direction when we introduce the reverse direction multi-decoder. I mean English to Uzbek and English. This will get the alignment information in the reverse direction, but it will not use any additional, it will not use any high resource language pair, right? Like Spanish English. But we will only get the information about the reverse alignment, reverse direction of the alignments. We are not getting as good as when we introduce Spanish to English, but we are getting slightly better compared to Turkish English. This result is not conclusive, but tells us if you don't have enough data, if you don't have any high resource language pair in the mix, maybe you should consider introducing the reverse direction alignment information into the model. And when we when we ensemble all these models, when we ensemble 6 of these models, we were getting 12.99, and we compared it with the conventional statistical machine translation model, and it was getting better in terms of with an ensemble. And just to give you an idea about the ballpark we're playing, Google Translate was getting 12.47 in this data set in this test set.
On the move from Uzbek to Turkish, could it be some of the benefit is obviously a lot more data in Turkish, so you're getting more alignments there, but they're also closely related languages.
Yes, exactly.
So
yeah,
you're going to get, I would expect that the alignment, the attention model would be better because of the relatedness of the two languages.
Yes, yes.
That was my question too. I was wondering if you had put Spanish English in first,
yeah,
how much?
Yeah, we haven't tried that test.
Yeah, I bet that Turkish English would still trump. Yeah,
We haven't tested that yet.
that would be an interesting one.
Yeah. One other question? No? Okay.
So did you have to change the sampling schedule so that it was oversampled Spanish and undersampled?
I will talk about that. And the Turkish English experiments, now we are not using Uzbek. We're not going to use Uzbek because it was really low resource. We're going to introduce Spanish and French by text in the same fashion. So this is our baseline. We are getting 17.28 blue scores when we just train a single pair Turkish English model, this model. When we introduce Spanish English, which has a lot of data, it doesn't actually get a huge improvement as we were expecting. We are getting a tiny improvement in terms of blue. When we add French English, again, the improvement is really, really small. This might be related with maybe the model has already saturated, maybe the model doesn't have enough capacity to learn something more, because French English was, we were using almost 50 million byte text on French English, and maybe we should have increased the capacity of the model to leverage the additional language pair for French English. But we got the best result when we introduce the English into Turkish and Spanish, the reverse direction model, the reverse direction multi-decoder model. And we ended up having 18.66 blue points. And when we ensemble 6 of those models, we were getting 22.56 blue points, which was way better than the conventional SMT model. Actually, this is even better without single pair models are also better than conventional SMT models. And the ballpark we're playing, Google Translate was getting 18.44 in this test set. So what we learned, adding low resource pair or linguistically similar pairs, if you for example, for Uzbek, adding linguistically close language pair helps a lot. And having high resource pairs is also important. But this applies only for some restricted scenarios. For Turkish English experiments, adding single pair improves the performance slightly, but we should have analyzed the capacity of how the model behaves as we increase the capacity and introduce more data. And where we were, luckily this year WMT16, there were Turkish English track, and we gave it a try. How our models behaving, how our models performing on WMT16. We are on unconstrained track because we are using 4 times larger byte text in Turkish English. We should note that. We are also using additional byte text from Spanish English and French English. These are the score. These are the results. The first rank, the entry was getting 14.45 blue score, and this is Johns Hopkins University phrase-based model. It was getting 12.9. When we use a single pair NMT model, we were getting, by using this amount of data, we were getting 12.8 blue scores. When we ensemble 4 of these models, we were getting 15.82. And when we ensemble 6 of multilingual models, we were hitting 17.8. Again, this is an unconstrained, it's in unconstrained track, but just to see how the model behaves on WMT16. So the question about the unbalanced data sets, this is a sketch plot. Let's consider 3 pairs. One of them is the amount of data, only 10% amount of data compared to the 100%, the pair 3. This corresponds to the red curve. And let's consider another model, another pair, which has 50% of the data compared to the pair 3. This corresponds to the blue curve. And the pair 3 is when we use all the available data. So what we see in this negative log likelihood versus number of iterations on validation set log probabilities, let's say. So we see the pair 1 converges and starts overfitting way earlier compared to the others. And we need to choose one model. We need to do we need to use a heuristic to do early stopping, right? So we need to early stop based on a criterion. We need to pick one model, one column here. For example, the model at the iteration 400 here, and then use this model to use in our test time. But this model is performing really poorly on all the other languages, right? We should have picked this model or this model, the model at this iteration for the blue curve, or we should have picked this model, the model at this iteration for the green curve. So this is not the ideal plot that we have. The ideal plot that we should have should look something like this. So we should actually delay the convergence of the low resource pair as long as we can, just to align with the high resource language pair. And then we will pick this model, the model at this iteration at 500, and this model will perform as good as this model will perform as good as all the other pairs as well, right? So this model should be the one selected by the early stopping. But we have to align these learning processes in a nice fashion. This was a sketch plot. Now let's look at the real plot. Here the dashed line corresponds to Uzbek English training. This is the validation the negative log likelihood on the validation set. Here the number of iterations and the negative log probability here. So the dashed line corresponds to Uzbek English, and the solid curve corresponds to Uzbek English again, but we do some tricks. We align the learning process, we actually adjust the learning process, we make all those pairs converge almost at the same time. And if we do these tricks, we choose the model at this iteration. If we don't do this trick, we will choose the model at this iteration. They're quite close in terms of log likelihood, right? But the problem is about the other pairs. This is a model coming from a Turkish Uzbek English into Turkish Uzbek English. We have 3 encoders and 3 decoders. So we have a lot of other pairs actually hidden in this plot. Let's look at other pairs. For example, this is for Turkish English. The solid green curve corresponds to the model trained with the Turkish English pair when we do those tricks. And the dashed green curve corresponds to the model that we don't do those tricks. And if we pick this model, as you see, this model is performing really poorly in Turkish here. But if we pick this model is also, if we pick at the model at this point, and we look at the solid curve, this model is actually doing quite good on Turkish and also in Uzbek, right? So we need to do some sort of balancing these learning. We need to adjust these learning curves nicely to choose a single model. And the trick was, how are you going to delay the convergence? You can introduce some noise. You can add some additional regularizations on the Uzbek English pair here. Or the easiest way of doing it is either you can play with the scheduling, you can oversample Uzbek English, or you can just reduce the batch size reduce the batch size on the low resource language, and then it will increase the noise in the gradient. It will also give you some sort of regularization, and it will also delay the convergence because you're going to use smaller batches. So this BB stands for balanced batches. This is just a trick that we use to align all these curves and to pick the best model. It's still just a heuristic, but when we look at the Turkish blue score, if we don't fix this, we're getting 9.57, and when we fix this, we're getting 13.91. It's a huge improvement for Turkish English. And I'll get back to that question. Why are we getting really the bad performance when we translate from English into other languages? It's related with this trick. We were not using this trick in the early experiments. We came up with this trick later on, and then we haven't applied it and replicated the original experiments on all WMT15 all experiments. So let's look at.
So how do you decide how much is it proportional to the, like if you have 10 times as much Turkish data as Uzbek data, your batch size in Turkish is 10 times the size of the Uzbek?
We were making them to finish one epoch at the same time. We were balancing the batch size according to that. We're reducing the batch size of Uzbek to finish one epoch at the same time with Turkish English.
So that would be the same.
Yeah.
So the Turkish batch size will, or excuse me, the Uzbek batch size will actually become smaller then.
Exactly.
And are you normalizing the gradients to be similar magnitudes between Uzbek and Turkish?
No, you're not doing so. And when we look at for example, English Uzbek and English Turkish, let's compare these two numbers. English Uzbek, these are really low scores. And when we translate from English to other languages, when we do this trick, even Uzbek improves slightly, but Turkish improves drastically. Here it jumps from 4.83 to 9.13. We should have replicated WMT15 experiments by using this trick again. But as I just told, it's taking a month to train the giant model. So yes, the lack of GPUs. And this was the first major chunk of my talk. Is there any questions up to now? Yes.
So I don't know if I missed that, but did you have a comparison to having separate attention and sharing just the encoders and decoders?
Yeah, if you don't share the attention, you will get better blue scores.
But that's not the same as the single model result, right? It's single model.
No.
Doesn't
But you just said
share.
if you don't share the attention, you'll get better blue scores?
Yes, you're gonna increase the capacity, and you're gonna specialize on that source target pair. Compared to, it's not compared to the, okay, let me tell you. You're gonna get better result compared to single pair.
Okay.
Not better result compared to multi-pair, multi-way model. Yeah.
Okay. Because I mean, like the attention is shared, but like the bigger thing maybe is that the half of the model is being trained on a lot of data. The source side of the target side is being trained on a lot more data, right? So
Yeah.
I mean, do you know, like, if you were to fine tune it on each one after doing the multi-training, have you tried that?
I haven't.
Like, do you think that would?
I haven't. Yes.
How does this approach compare in terms of quality improvements for low resource languages when to the approaches where you basically pre-train on one language pair and then basically steal the weights and then start on a different language pair?
We did some experiments in the context of Lorelei, but I don't think I should. Yeah. Let's take it offline, maybe. Okay. Any other questions?
So I think Christine was saying, what happens if you totally... It feels like there's a range of things between having one complete shared attention model and one attention model per language pair. Mm-hmm. And in fact, you had one set of experiments where you gave a one-hot encoding of the source language, right?
Yes.
As an additional parameter. It feels like you could also do things like give one-hot encodings of the target language, or have some portions that are shared for all language pairs and some portions of the parameter space that are shared for all language. It feels like there's a broad continuum here that would allow you to learn some specifics about how the word order changes for specific language pairs, but allows you to share things. And I wonder, like, I see how a single shared attention model is really attractive from a zero resource standpoint. But in practice, oftentimes we do have some resources. And I wonder to what degree, like, so in the case where you added a one-hot representation of the source, do you know if that added anything? Did removing it harm the blue score?
Not really.
So it doesn't seem to make much difference in,
Yes.
in practice.
Yeah.
Are you going to talk about pivot in the zero
I
resource?
will. Huh? Yeah, the second part I will be talking about multi-source explorations and zero resource explorations. So can we actually, so we train this huge model, but can we actually use it to do something else, right? Can we actually do can we actually do multi-source translation by using this model? So we showed a way to do one-to-one training and one-to-one decoding, like using only byte text during training and also using byte text using only one source during decoding, right? But can we actually do many-to-one training or decoding? During training, we might have Spanish and French at the same time, and we can train the model by using these additional information. Or we will not have access to the multi-source, this multi-text during training, but maybe only test time we are allowed to use this multi-text. And the first approach was actually explored by Baretsov. I mentioned that at the beginning of my talk. They were doing multi-source translation, but they were needing the model necessitates multi-text. And if we just use bilingual corpora to train the model, can we actually decode using multi-way data during test time? So the model will be trained only by using only byte text, but we're going to decode. But during test time, we will have access to multi-text. This is the scenario on news test, if you're familiar. So you're given access to all news test sources. You can actually use all news tests in your development or test set. Or can we actually train this model by using syntactic multi-way data? Because we are training a multi-way model, so we can actually generate our own data in a syntactical. It will be a pseudo-parallel corpus, and we can maybe use this model, use this generated data back in the model to do multi-source decoding, either during training or at the test time. So I did some proof of concept experiments on MNIST. You can laugh here. In MNIST, you can split the digit into two. Let's say the top half and the bottom half. This is the way that we train our regular multilingual model. So we are only giving the top half in one iteration. And then in the next iteration, we are giving the bottom half. This corresponds to, let's say, Spanish English, and this corresponds to French English. But we can also have the both of them together, top half and the bottom half, and we can actually model probability of y given x1 and x2 at the same time. So here, how are we going to do this? Depends on the merging operation that we should introduce here. So you are given access to two information sources. You will end up with two context vectors right after the attention. And how are you going to mix those two context vectors? So I did some early experiments. There are two ways of doing this. One of them is the late averaging. You can actually you're given two sources, but you can treat it, you can first feed the first information source, get the probability of y given x1, and then you can provide the second one, and then get probability of y given x2, and then you interpolate these two probability distributions. That corresponds to late averaging, and it's actually similar to model ensembling. Or what you can do is, you can introduce an additional operation here that we will call it merger layer. And you can actually combine the representations coming from two sources here, and then estimate the probability of y given x1 and x2 simultaneously. And we did some early experiments on MNIST. Just to give you an idea, this corresponds when we use the right branch. This curve corresponds to when we use the left branch, and the red curve corresponds when we use both branches. This is the training set error we get on MNIST. I'm showing this because we will see a very similar plot soon. And what is the basic setup that we have? We will have two single pair models, two single pairs, Spanish English and French English, Spanish English and French English. And we will train the model using only byte text. We will also have another set of experiments that we will have access to Spanish and French at the same time, and we will train the model using this multi-source fashion. Again, the whole point is how are we going to define this merger operation in between when we do multi-source translation. So it's fairly easy. We are again using the shared attention module here, but it's going to attend first the context set, annotation set C1, and it will generate the time-dependent context vector C1, and then it will attend next the second annotation set. it will give us the time-dependent context vector C2. And we will define some operations, for example, some arithmetic operations to merge these two context vectors together. Or we can define another attention layer on top of these context vectors to actually gate one another. It's going to be a hierarchical attention module. Or we can just concatenate them and feed that into the decoder. This is the plot when we train Spanish English, French English, and the multi-way model. The red curve corresponds to the multi-source model, and the other curves correspond to the single pair models. This is pretty much, very much similar to the MNIST curves. So this actually encouraged us to work on multi-source translation. That's the story behind. Let me talk about the experimental setup first. So we have already trained this model. It's a multi-way model. It has one multi-encoder, French, Spanish into English, and English into French and Spanish. We're going to use 34 million for Spanish English and 65 million English to French as a bytext. And we're going to evaluate them on news test 13 and 14. Question? No? All right. And we're going to use only bilingual data to train this model. And we're going to test it by using multi-text only during decoding time. So this model has not seen any multi-text during training, but only during test time. So we, just to remind you, we have early averaging, which necessitates a mechanism here to merge two information sources. And we have late averaging that actually interpolates these two probability distributions. So what happens when we do single source translation? We train this giant model. This is a multi-way model. It has 4 pairs, Spanish English, French English, and the other ways. Let's just look at Spanish English and French English. When we use the multi-way model, we're getting 28 for Spanish English and 27.9 for French English blue scores. What happens when we test it using multi-source data? So this column corresponds to when we use multi-source translation on test time. So it jumps all the way up to 31 blue points when we use only early averaging. When we employ late averaging, we get 31.57. And we can actually merge these two together like another ensemble. We can ensemble these two, first two rows. And we end up with early plus late. And we can achieve 31.88 blue scores without even training using multi-text by using the multilingual, multi-way model. But surprisingly, when we train single pair models for this model, for example, when we train one Spanish English and one French English single pair models, and then we ensemble them together, it also gets quite good scores. This 31.46 corresponds to that model. This is just ensembling one French English and Spanish English model, 2 models, sorry.
So in the case where you just average them, you average them like somewhere fairly deep in the network, even though it wasn't trained that way, and it just worked?
Yeah, it just works.
That's cool.
When we just do very simple operations, arithmetic operations like mean, it works surprisingly well. I will get to that point. We have some speculations about that. So what we learned from these experiments, we actually don't need multi-way parallel data during training. But if you have multi-way parallel data, it will converge way faster. Why it works? Because we alternate between, for example, French English and Spanish English. It tends to learn a common context vector space because it cannot actually overfit on one language, because in the next update it will get the other language. It will get the update on the other language pair. So it tends to learn a common vector space right after the attention module. And such smooth vector space allows us to do very primitive arithmetic operations like mean. That is the rationale why why this mean operation works. For example, max, min, they just don't work because we're not encouraging sparse representations or something. When we just do sum, it doesn't work as good as mean. We can also speculate if we have flattened the manifold higher at that level. If we are on the manifold, if we represented one source sequence into one point in that manifold and the other one in the other point, and we interpolate between these two, this gets us a better representation. This is a speculation that I'm exploiting the idea of manifolds. What we could have done more, we can actually use the generated data to fine-tune the multi-way model, because we can generate we can generate multi-way data. It's going to be pseudo-parallel data, but we can still use it. And we don't know how this extends when we increase the number of encoders, when we increase the number of sources that we have. Currently, we only use 2 sources, but we can extend it up to 6 with the latest UN corpus, or we can extend it even more by using Europarl, for example. So the last topic that I will talk is going to be about zero resource translation, which we are going to combine all the tricks that we have together to do zero resource translation. So I was always asked, how does the model behave when you train this model? What if you just ask to translate between Spanish and French at the test time? This is called zero-shot translation, and we're getting almost 0 blue points. Not 0, but barely 1 blue points. But actually, Spanish to English and English to French is kind of promising. This is the pivotal path. For example, we're first going Spanish to English and English to French. This gets us a decent blue score. On the test set, we're getting 20.4 blue scores. So this is going to be our baseline, and we will try to beat this baseline by using zero resource pair, this pair. So what we have is we are given this is highly influenced by the idea introduced by Rico Senrich. The idea is using back translated data to fine-tune or to even train more your neural MT system. So we are given English to French, and we have this multilingual model. We can use the English site to generate some Spanish data, and then use the Spanish data here to fine-tune the Spanish-French path. Note that we were also given this bytext, so we have French and generated source Spanish. We can actually fine-tune this path and then do the zero resource translation. This is not zero shot, but zero resource, because we're only using bytext available during training. And all the data generated here is pseudo-parallel data. So what happens when we do this? We tried it by generating 1K, 10K, 100K, and 1 million pseudo-parallel corpus, and we compared it with the true parallel corpus. So what happens is that when we use 1 million pseudo-parallel corpus, we were able to get 70.61 compared to 20. This is pivotal translation, the score of the pivotal translation. This is the score after we fine-tune our model using the pseudo-parallel data. If we use the true parallel corpus, we were still not getting as good as, blue scores as good as pivotal translation. We were getting 19.97. We still thought, okay, we are lacking some tricks. By the way, we were fine-tuning.
What's the 20.35?
Which one?
The second, on the true parallel, above that.
This one?
Yeah.
Yeah, this corresponds when we used 1 million data, 1 million.
Actual Spanish data?
Actual, yes. And then we train a single pair model. This is a single NMT model that uses this amount of data, just to compare with these numbers. And also, this model is doing better pseudo-parallel corpus. When we generate pseudo-parallel corpus, this amount of data, it performs better than when we use the true parallel corpus, because this is noisy data, and noisy data inherently regularizes the model when you train it, and it also has some inductive bias of the model. This is speculative, but yeah, these were our conclusions. And how can we actually beat the pivotal translation by using only pseudo-parallel corpus? There comes the multi-source translation to our aid. So the idea is simple. We shouldn't be only training the zero-resource pair. We have another source of information. We have a well-trained, let's say, Spanish-English model, right? Or sorry, we have a well-trained. Let me get back to here. So we have a very well-trained English to French model here. But when we're doing the translation from Spanish to French, we're not using this source of information. Maybe we can use this multi-source path to teach the zero-resource pair here, right? So think about this multi-source pair. There is a multi-source pair here, English, Spanish into French. This is going to be our multi-source teacher, and we're going to teach Spanish-French pair to learn the context. Where should you put the context representation in that manifold, let's say. And we're going to only fine-tune the alignment parameters. And when we, this corresponds, these experiments, all these 3 lines corresponds to those experiments. Sorry, the last 2 lines. We generate the Spanish English to Spanish. We will use the Spanish data, and then we will not only fine-tune the Spanish to French path, but we will also fine-tune Spanish English into French path, and we are going to interleave between these 2 computational graphs, and hopefully teacher will teach student how to translate between this zero-resource pair. When we do that, by using 1 million pseudo-parallel corpus, we can achieve, by early fusion, we can achieve 21.46, which is better than zero-resource, better than pivotal translation. And when we use true parallel corpus, we can get a little bit better results than when we use pseudo-parallel corpus. This is a way of combining everything that we did to do zero-resource translation. This is not the ultimate way, and it's still ongoing. We just generated 1 million data and then fine-tune, but it should have been done in an online fashion. Generate this amount of data, use this data in a couple of epochs, and then generate again, and then fine-tune your model, generate again, so on.
Also, is this, you're calling it a student-teacher model, but isn't it really ensembling? Like, it's the ensembling technique that you're basically summing up. You're explicitly decoding Spanish into English, and then using that the same way you used before, right?
Let me draw it. So,
because actually the technique you described before didn't even do anything special at training. Like it wasn't even trained with multi-source. So is this one actually trained with multi-source?
Yeah, it's not even trained with multi-source data. We are only fine-tuning it with multi-source data.
So there's no actual multi-source data.
No, there is no
generating multi-source.
Yes,
data.
yes.
And then at test time, you're still providing the single. It's not
at test time,
multi-source
you're
data.
still we're giving one. We're not providing multi-source data during test time.
Well, you're not explicitly, but are you actually decoding into English and then?
Yes.
Okay.
Yeah.
So, does that happen at training time too, or is it training? Is it just?
Yeah, it happens in the training time too. We generate this amount of data, right, by the model, 1 million data, and then we are going to use this data. We have access to Spanish-French data as well, right? And we had English to French data as well. So we can do, let's say this is English into Spanish, and we have French. So we were only given access to this data. We will generate some Spanish, and then we will use this generated data. We can use it in 2 ways. We can just maybe update this path, right? Or we can also update this path, right? By using this merger operation here. So this is what we call the teacher network, and this is what we call the student network.
I thought it was not parameterized. I thought it was just a summation.
It's summation, yes. But this is a different computational graph. But it uses a very primitive operation. That's why I call it.
What is the difference between what you're updating in the single case versus the multi-source case?
We are only updating the alignment parameters, the attention module parameters, in both cases. Yes. Yeah.
I mean, how does it compare? So, did you do just if you were to just do pivot and basically do ensembling, because before you would show that just doing ensembling works almost as well as doing the early thing.
Yes.
So do you think that's the same case here?
So we haven't done that. We haven't done that experiment. Any other questions? No? All right. So what we have learned, we don't necessarily need a direct resource. So we can generate our own resource by using the multilingual model. And multilingual model naturally embeds multiple decoding strategies, even if you trained it by using only by text. But it took 1.5 years. This was our initial goal when we started actually the multilingual neural machine translation. That's why we stick to the idea of shared attention all the way from the beginning. And what more should we do? We should do some active learning to bring additional gains. And maybe by using maybe using additional pairs and throwing a lot of data, maybe the attention function, this alignment function, can generalize to the unseen pairs, unseen points in its intrinsic space. And then maybe if we throw enough data, we can do zero-shot translation, but that should be explored more. And we should definitely explore direct translation more. I mean zero-shot translation. And one point is we assume that we already have very well trained encoders and decoders for example, Spanish, French, and English. And some ongoing work, what we can also do using this multilingual and multi-source model, we can train a model to learn system combination. Let's say we have a phrase-based, a Hiero, an NMT, and multilingual model, and they're all models from German to English. You can learn another multi-source machine translation model on top of it to actually learn to do the system combination. This is an ongoing work, but the operation here changes. You should be using some other type of operation, and this time it's a parametric function. Or you can do larger context neural machine translation. Let's not consider only the center sentence to do for example, Chinese to English translation. You can introduce some previous NBEC sentences, also some future context sentences. And again, you should be using some other type of operation here, but I'll show you what happens if we just use mean here. This uses the new released UN corpus. We're still doing some experiments on Spanish English and Chinese English. These curves correspond to Spanish English. We use mean as the merger operation, and we consider the context window of size 0, which means no context. Context window of size 1, which uses 1 left and 1 right context, 2 and 4. This red curve corresponds to when we don't use any context. Here, this is the negative log probability on the validation set. When we use the context window of 1, that corresponds to the blue curve, and we have almost 5 points of negative log likelihood difference. When we use 2 as the context window, when we use context window 2, it actually converges a little bit later, but it almost gets the closer scores to the context window of 1. And when we use context window of 4, it actually gets almost the same thing with the context without any context. This is because of the operation that we're using. Taking the mean is not the best thing if you're doing, if you're extending your model to do larger context. of course, if you're extending it to up to 4. And we can actually use the multi-source, we can introduce another type of operation to leverage, to improve the performance when we do English into some other languages. Because we always see improved performance when we translate into, for example, when we translate in a multi-source fashion. We can leverage this fact to improve the performance when we translate English into Spanish. And this, what if we don't have any data in this language? Let's say they introduced us a new language and we don't have any byte text, or we have a really tiny amount of data to be used. So what we can do is we can train a hybrid encoder, which is, in this case, it's a character-based Romanized input. It gets character-based Romanized inputs, and we train it with a mixed batch of all these languages. And when the new language is introduced, we're just going to Romanize this new language, and we're going to feed it into a character level and do the translation. Thanks to DARPA, I think they made the LE in Encoder because of all these low-resource languages. I know. At the end, so multilingual NMT pros, language transfer towards low-resource language. This is one upside. It enables multi-source translation out of the box. It also enables us to do zero-resource translation with pivots. It naturally embeds multiple decoding strategies. Pseudo-parallel corpus can be generated by the model itself. And it's flexible and compact, easily extendable to other modalities. This year, WMT15 multimodal challenge uses a very similar architecture. Got the first score on multimodal challenge. What are the cons? Scheduling still relies on some heuristics, and the architecture seems a little bit complicated. We should maybe prune out. We should use simpler architectures, and it's taking a really long time to train these models. If you make a mistake, you just trash hours of GPU time, and the only thing that you will be you have contributed is the global warming. So, yeah. So what lies ahead? This is the last slide. So are we optimizing the right thing? Should we be optimizing log likelihood and then look at evaluate our model on blue? So there's a lot of things going on, a lot of explorations going on. What should we be optimizing? And another problem is if you're going to optimize log likelihood, but we're still going to decode using beam search, let's say, how are we going to achieve diversity in the beam search? Or how are we going to achieve faster decoding? These are other problems. And the granularity in our input or output spaces. Should we be using all the experiments that I showed here? They're all using byte pair encoding. But should we be using bytes or characters or Unicodes or something else? This is an unanswered question. But at the end, if you want to surpass the human level quality, we should have human in the loop. We should be, at the end of the day, we care about the human evaluation. We should have some mechanism to feedback the human evaluation into our model and improve the model itself by using the human evaluations. And this feedback signal and how are we going to use this feedback signal is really important. And at the end, I really feel like all these courageous steps, taking us closer to the language barrier, and I think we're quite close. And thank you for your attention. The code, almost all the code is available on DL4MT Habitat. So this is the tutorial for neural machine translation. This is character-based decoder. This is multilingual model, and large context implementation is also it's coming soon. We are maintaining these code bases, so feel free to send emails or opening up a PR or sending issues. And thanks a lot for your attention. Thanks.